Hello students, welcome to Saurabh's classes. So in this video we are going to discuss about group. Okay, so to know group, first of all we have to know about binary operation. Okay, so let S be a non-empty set. Okay, S be a non-empty set. A binary operation on S is a mapping if such that S cross S to S. Okay, so binary operation is a mapping from the Cartesian product of S cross S to S. So it means it is taking two elements of S to another element of A. Okay, that is f of AB belongs to S, where A comma B belongs to S cross S. Okay, now this binary operation is denoted by, sometimes it is denoted by this composition, this star, this plus circle, this plus, this minus circle. It has lots of notation. Okay, but a binary operation means is taking two elements, it is taking a pair of elements A comma B to an element of. So a binary operation means it is taking an element from S cross S to S. Okay, so let me give you some examples of binary operation. Let star from Z cross Z to Z defined by A star B is equal to A plus B plus 1. Okay, so if you, when you are taking two integers, then A plus B plus 1 is again integer. So this is a binary operation on Z. Okay, let me give another binary operation on R, that is composition from R cross R to R defined by A compose B is equal to AB. It means the product of two real numbers, the usual product. Okay, so again this is a real number. So this is binary operation. Now let us talk about group. Okay, let S be a set. More precisely, S be a non-empty set. Okay, S be a non-empty set. Let composition be a binary operation on S. Okay, so composition is a binary operation of S. Then S is said to be group with respect to this composition if S satisfies the following. If satisfies the following. First property is, when you are taking any two elements from S, that is let A comma B belongs to S, then A compose B must belongs to S. Okay, that is composition of any two elements of S again in S. This property is actually known as closed property. Okay, observe that. Let me give you some examples. When you are considering about natural number and you are defining an operation, binary operation, that is A compose B as A plus B. Okay, so we know that addition of two natural number is again natural number, that is if A belongs to N and B belongs to N, then A plus B again belongs to N. So we can say that natural number is closed with respect to this binary operation. Now, if we are defining an operation as A compose B as A minus B. Okay. Now, if A belongs to natural number, B belongs to natural number, then A minus B may not belongs to natural number. Let me give you an example. That is 2, 3. These are two natural numbers, but 2 minus 3 is equal to minus 1, which is not a natural number. Right? So we will say that natural number is not closed with respect to this binary operation, but natural number is closed with respect to this binary operation. Okay. So for being a group, S need to be closed with respect to that binary operation, that given binary operation. Okay. Next property, this composition must be associative on S. This composition must be associative on S. What does it mean? It means if you are taking three elements, let A, comma B, comma C belongs to S, then A compose B compose C is equal to A compose B compose C for all A, B, C belongs to S. Okay. Then this composition must be associative on S. Okay. This is the second property. Let us discuss about the third property. This S must contains an identity element with respect to this composition. Okay, this S must contains an identity element with respect to that composition. What does means by an identity element? By an identity element means that let identity element E. Okay, so what does mean by the identity element? Identity element means A compose E is equal to E compose A is equal to A for all A belongs to S. It means we are having this A, not E. So this E is a fixed element on S. Okay, so A compose E is equal to E compose A for all A belongs to S. Now observe that if you are considering an binary operation on Z as Z cross Z to Z by A compose B as A plus B, then I will say that the integer 0 is the identity element, on Z, as A compose 0 is equal to A plus 0 is equal to A, right? And 0 compose A is equal to 0 plus A is equal to A. It means A compose 0 is equal to 0 compose A is equal to A. And this result is all for all A belongs to Z. Then I will say that 0 is a identity element of Z with respect to this composition. But if you are changing the composition, then you will change the identity element also. As if you are considering a binary operation on Z cross Z to Z as A compose B is equal to AB, that is product of two integers, then I will say that then this time the identity element is 1. This identity element as A compose 1 is equal to A into 1 is equal to A, and 1 compose A is equal to 1 into A is equal to A. Then I will then A compose 1 is equal to 1 compose A is equal to A. Then this time 1 is the identity element. It means if you change the binary operation, you will get different identity elements. But for a fixed identity element, S must contains an for a fixed binary operation, S must contains an identity element with respect to that binary operation. And fourth is for any A belongs to S, there exists an element B such that A compose B is equal to B compose A is equal to E. For any element A belongs to S, there must exist an element B such that A compose B is equal to B compose A is equal to E. then we will say that if F satisfies these four property, then we will say that this S is a group with respect to that composition. Okay, that is this S compose is a group. Okay, now with this four property, S satisfies commutativity. That means for any two elements A comma B belongs to S, A compose B is equal to B compose A. For all AB belongs to S, then we will say that S is a commutative group, that is S compose is a commutative group or abelian group. Okay,